Ladies and gentlemen, we took a look at that data. We're asking, why does decreasing pH affect juvenile and adult oysters differently? And part of that has to do with the speed of reactions, and that has to do with collision theory. Okay, so collision theory states that reactions, like the degradation that acids cause, they only happen when things collide with the right amount of energy in the right direction. So if it's too slow and we have insufficient energy, the reaction won't happen. If it's the right speed but they're in the wrong orientation, the reaction won't happen. So if we want reaction to happen faster, it's all about increasing the number of collisions. So I'm going to give everybody this page, but we're going to talk through the nitty-gritty of it over here. So that's our question. Why does decreasing the pH affect juvenile and adult oyster populations differently? And to answer that, we need to think about how can we speed up reactions and how can we slow down reactions. And Ms. Schrock is going to pass out this paper to you, and it goes on 128, and then we're taking our notes on 129. So I know many of you are working on your labs right now. If you need to watch this later, you may, but if you have the capacity to take notes while something is filtering, please do. So how can we speed up a reaction? Because that data from last year was just over a couple of days. Who knows, if the adult oysters had stayed in that water for a long time, what would have happened? But it looks like it's a reaction speed question. And then the other side of that question would be, how can we slow down a reaction? And certainly when it comes to the oysters being destroyed, that's the question we want to be asking. Okay, so we're going to take a look at, chemically, what can we do to increase the number of collisions or decrease the number of collisions to either speed up or slow down a reaction. So one of the things we can do to get more energy into these collisions and speed up the reaction is we can stir the reactants. And that's one of the reasons your procedures involved stirring, a lot of you. It's also the reason that if you're making lemonade or something like that, you stir the water and sugar to get the sugar to dissolve faster. You're adding more energy, making those molecules move faster. That gives you more energy in the collisions and a faster reaction. And for anybody watching in the future, there are 20 humans in this room doing lab work utterly silently so that we can get a good recording, and I appreciate them so much. So here we go. Faster molecules. Means more energy, means more collisions at the correct energy level or at a high enough energy level, which means a faster reaction. So, by contrast, if we were trying to slow down the reaction, what could we do? What do you think, Kason?
We could not stir.
Right, we could let it rest. Okay, you can think of that a little bit like if you've ever heard the idea of quicksand. Like if you fall into it, you're supposed to stay very, very still. That's because you're literally slowing down the energy that would pull you under. Same thing here. Slower molecules means fewer collisions, means slower reaction. Say it again? Yeah, like oobleck, a little bit. All right. So that's one thing we could do. What's another way, though, that we could increase the amount of energy in that system? How can we increase the amount of energy in that system? What do you think, Abby? What's another way we could increase the amount of energy in that system to get us more collisions? Well, let's think about the types of energy that we've got available to us. That's back on Unit 2. Let's think about this. We got a lot of different types of energy. Let me find that page for us. It's been a minute. Okay. What can we do to increase the amount of energy? We've already tried motion. Yeah, we could absolutely heat it up. That would definitely add significant energy. So we could increase the temperature. And this is another reason why you don't add the ice to lemonade before you start stirring in the sugar. If you add ice to your lemonade and then try to stir in the sugar, it'll take a really long time to dissolve the sugar because it's a much lower temperature. So higher temperature. That's right, you can even use hot water and then add ice later. That's the way to do it. More energy means faster molecules. Again? 129. We're on 129. And so I'm going to go ... on that one because it's the same as above. More energy is faster molecules, more collisions, and a faster reaction. And so if you were trying to make the world's worst lemonade or Kool-Aid or Crystal Light or whatever it is you're making, the worst thing you could do to slow down that reaction and make you wait all afternoon for your drink is to decrease the temperature. And I'm actually going to leave that blank for you to fill in your own reasoning on that one. There are a couple other things we can do, though, that are less related to energy and more related to the actual amount of collisions that are happening. So let's imagine we took everybody out of this classroom except for myself and Ella. And we just ran around with blindfolds on. What are the chances she and I are going to run into each other?
Very high.
Okay, truly, we chose 2 ADHD people, so actually probably pretty high. Let's pick 2 people that are on the calmer side.
Let's do Lauren.
Okay, Lauren's on the calm side, I would agree.
And Cooper.
Okay, Lauren and Cooper are both on the calm side. If we blindfold them, have them walk around the room, the chances that they're going to run into each other are on the low side. They've got a lot of space. However, if I blindfolded all of you and put you in this room and told you to run around, what are the chances you're going to run into somebody?
Very high.
Much higher. What we did was increased the concentration of the reactants in that reaction. So the more reactants you have, the higher the chance of collision. And so once again, more collisions is going to be a faster reaction, but in this case, it's not more energy that's causing it, it's more particles. Okay, so that's another thing we could do. If we were trying to get more people, oh, I'm sorry. Let me calm down for a second. I see people writing. What's the opposite of increasing the concentration of reactants, Kason?
Decreasing.
Right. If we want fewer collisions, we'll have fewer people in the room. Same thing in chemistry. If we want fewer, less reaction, we're going to have a lower concentration. And so the logic here would just be the opposite. Fewer particles means fewer collisions. There is another thing we could do. let's say we did pick two very high energy people. Ella and myself running around this room with blindfolds. The chances that we run into each other, truthfully, pretty high.
And the chance that we run into a wall is
Also really high. What could we do to make it less likely that Ella and I will run into each other if we've got to be running around blindfolded?
we have
More room.
You.
Exactly. We could put us out on the football field. Wait, did you say remove me?
It's a drug you.
Drug you.
Both of you.
Okay, so that would be
Sleep.
an example of decreasing the temperature.
Yeah.
Less movement. Okay, so ladies and gentlemen, we could move Ella and I out to the football field, put us in blindfolds, let us run around. We're going to have way fewer collisions. And in that case, that is an example of decreasing the concentration of reactants. Okay, so it might be you use less of the reactants, it might be you give them more space to run around, so it might be more stuff in the solution. So I just want to keep that in your mind. There is one more thing we could do, though. And I can't use people for this example because it's going to be kind of gross. Let's imagine, oh my gosh, I just got chickens. Can we use my chickens as an example? They're adorable. Okay. I don't know if you know this, but there's a type of chicken called a Jersey Giant. It is about 10 pounds, and this sucker looks like it could take on a toddler. They're very calm, very kind, but it's a big chicken. That's 10 pounds of chicken. Let's imagine, currently my chickens are living in my bathtub because they're very little and I can't put them outside yet. Also, it's really cold. Let's imagine I had 20 pounds of Jersey Giant chickens in my bathtub, and they're running around. Are they going to run into each other?
Yes.
Yeah. We're probably going to get one collision maybe every minute or so. Okay? My bathtub's pretty big. They got some space. So that's 20 pounds of Jersey Giant chickens. What if instead of Jersey Giant chickens, I used little tiny baby adorable chickens? Have you ever seen baby chicks? They like fit in your hand, they fall asleep, they're adorable. How many chicks do you think it would take to get 20 pounds of chicks? A lot.
200.
Maybe 200 chicks. Okay, they're really tiny. I mean, you could toss them. You shouldn't, because that'd be unkind, but you could. So let's imagine I put 20 pounds of baby chicks in my bathtub. What are the chances we're going to get some collisions then?
Oh, very high.
Really high. What we actually did, and don't laugh at me here, we technically increased the number of particles, but another way to think about that is we increased the surface area of the particles. There's literally more surfaces of chicks that could run into each other than when we had the two big chickens. Okay? As a less gruesome example of this, because we don't want to think about grinding up chickens, when you're trying to make lemonade, if I gave you a giant sugar crystal and told you to make lemonade with it, would it take longer or shorter time? Right. That would take forever to dissolve. What if I gave you powdered sugar instead? Much faster. And what's happening there is that we're increasing the surface area of the reactant. So this is one where I kind of have to go to the molecular level to make the analogy make sense. People definitely doesn't make sense for this one. Chickens makes some sense. But truthfully, what we're talking about is grinding up a material so that you have a ton of surface area that's available to have a collision. So here we go. I don't have Jersey Giant chickens. I'm a little sad about it, but I'm going to be okay. I do have one of those, yeah. So when you have one big chunk of reactant, it's going to have very few collisions because it's just essentially operating like one particle. But if you grind it up and increase the surface area, you get more exposed particles, which means more collisions, et cetera, just like above. And so then the opposite would be decreasing the surface area. If you use one giant chunk of sugar to make your lemonade, the reaction's going to happen really slowly because there's not a lot of surface area, available for collisions. So I left these blank so you could do a little bit of thinking and fill in your own logic here, but it's going to be the opposite logic as the column on the left. Now, there are a couple of other things we could do to speed up a reaction. We're not going to talk a ton about these at this point in the year, but I do want you to be aware of them because they might be helpful to you when you start talking about your reasoning on different things. You can also, like we talked about with making the room smaller, you can increase the speed of the reaction by decreasing the volume. You can also increase the number of collisions by increasing the pressure. You could also add something called a catalyst, and that helps lower the amount of energy required for the reaction, which speeds up the number of successful collisions. So I think these thoughts will be helpful in figuring out why decreasing the pH is affecting juvenile and adult oysters differently. I've got next door to this page, we've got information about making a chemical reaction happen faster, and I think it would be a good idea for you to read that. It sort of summarizes a lot of the ideas that we talked about on this page. And I'm going to pause this recording here.